I'm presenting some work like that I started during my PhD at EPFL together with Jain and Marilyn. And then I applied some of the improved color models to predict glare in colored scenarios. So I'm presenting both the experimental part that was done at EPFL and then applying different color models and trying to see which one works. So it's more of experimental work rather than simulation, just because, yeah, like keeping up with everyone else's presentation, which was more on the simulation. Yeah, it makes me a bit nervous that Jan is also online. Okay, so I think, yeah, David already explained really well about the glare metric and the definition of glare, so I won't go through that. So mainly the information I want to convey here is that usually glare models are developed based on the user assessment surveys, the one that's shown here. And these are then statistically matched to the photometric and the physical properties of the scene, mainly the geometry of the glare source and the luminance and illuminance. The one example shown here is the daylight glare probability. So these models are able to predict glare for a group of observer pretty well, but there are certain lighting scenarios under which these model fails. One of them is the colored scenarios. So when you have a colored lighting source, these models tend to perform not really well. So we did some experiments earlier with the electrochromic glazing, comparing the electrochromic glazing with the color neutral glazing. And this was the work that I had presented in last Radiance workshop, not the last, the year before in Bilbao. And we did found that the blue colored electrochromic glazing is perceived more bright and discomforting compared to the color neutral glazing. So it's kind of an extension of that work. So here I'm trying to look into more different colors, not just blue, and trying to find if there is an influence of color of daylight, which is filtered by a different glazing color on discomfort glare, and comparing the red, green, blue color with the color neutral scenario. So here in this picture, you see some of the sample experiments that I did with the participants, and each of the glazing have similar visual transmittance. The color is the only thing that is varying between different glazing scenario. So the experiments were designed to have around 55 participants. These were university students aged between 18 to 31 years. And the study was designed as within between mixed vectorial design. So the color was changing within subjects and the transmittance of glazing was changing between subjects. So we used two different level of transmittance. And the question here was trying to determine whether glare source color in combination with the glare source luminance have an impact on glare perception. So in other words, will people perceive glare differently, even though the luminance of all of these scenarios is same, and only the color is the element that is changing between these scenarios? So yeah, this is the experiment protocol. So basically, there were like two sets of participants, 28 in each group, and then each group experienced 4 different scenarios of colors. And then the transmittance was changing between the participants. So one had a high transmittance value of about average 2.5%, and then another one had a low transmittance of 0.37%. And this transmittance was only changing for the colored glazing, the one that you see here, and the rest of the glazing were at similar transmittance. And then only one glazing was colored. So to maintain a normal color perception within the room, we did not change the color of all the glazing. And this window kind of moves depending on the sun position. So sometimes it's this window and this one, or other times it's the most right one. It depends on the position of the sun. And all of these experiments were done in winter from December to February to have a low sun angle, which is visible behind the glazing, and it's creating glare. And we try to maintain similar daylight condition between the experiments. And the experiments were conducted on clear sky days without any clouds. And this is the protocol that we followed. So the participants will come and do some baseline measurements in electric light. Then they will be exposed to a daylight scenario for a few minutes and answer some questions about glare. And this will be followed by a break. And then the same process was repeated 4 times. And all of the scenes were counterbalanced between each of the person. So they never saw them in a similar the order was not maintained similarly for all the participants. So now looking at the glazing properties, we try to have similar glazing transmittance for all of these colored glazing, but their spectral characteristics was changing depending on which color it was, and we try to have distinct spectral characteristics. So this one here, you see the blue glazing and the green and the red glazing, and the spectral shape is kind of similar between both the high transmittance glazing and the low transmittance glazing. And all these were measured in a lab environment. And this is how the glazing color looks like against a D65. So you see this one is the green and the red, color neutral, and the blue. So I will jump to the results. So when we measured the vertical illuminance for all of these 8 scenarios experienced by 55 participants, we observed similar level of vertical illuminance in the high scenario and also in the low scenario. So these are the scenarios where the transmittance was low, and these ones are the high, and you see the color also on the x-axis, and these are the vertical illuminance. So you do see there are some variations in the vertical illuminance, but I think they are within a range. So I think it's within, yeah, so within, I think, 10 or 11%. This is due to also the differences in the transmittance of the glazing. And this is how the sun luminance value looks like. So the sun was the main glare source in these experiments. These are the high situation, and these are the low situations. And here you see a false color HDR image of the high and the low scenarios. So the goal here was to maintain similar glare conditions, so similar luminance, similar illuminance, position index, and the size of the glare source, that all of these elements stay similar within the colored scenario, and the only element that's changing is the color of the glazing. So same goes for the glare metric value. They were like about 0.51 to 52 for the high scenario, high transmittance scenario, and for the low, it was between 0.37 to 0.39. So looking at these glare metric values, it seems like, yeah, people should perceive all of these colors similarly, because the glare model was predicting it at the same level, but this is not what we saw in people's subjective response. So this is the distribution of response when people were answering the question, are you experiencing any discomfort due to glare at the moment, on a binary yes-no scale. And you can see here, we also found similar responses when measured on a different scale. So this one is the 4-point scale, going from imperceptible, noticeable, disturbing to intolerable. So again, similar results. The red and the blue glazing were quite more disturbing compared to green and the neutral. So here it does like show us that the glare metric doesn't work for these scenarios, and the influence of color was statistically significant, which with a large effect size between, like, if you compare the neutral with red and neutral with blue. So it also indicates that how we use luminance with a V lambda weighting function doesn't work here. So glare model use luminance as a way to incorporate spectral characteristics. And in the V lambda function here, the sensitivity peaks at the green, and the sensitivity is quite low at the short wavelength and the long wavelength area, whereas this is not what we found in these experiments, where people were experiencing more glare in the blue and the red glazing scenario. And here it's the spectral characteristics of the sun, which was measured from inside the room when the experiments were taking place. So again, you can see the spectrum is quite different, and what luminance predicting here is very similar for all of these scenario, which is expected when using a V lambda curve. So after this, we try to apply different methods, alternate methods to V lambda to characterize the luminance and glare for such scenario. So to apply different V lambda or use color appearance model require us to first measure the sun spectra, a glare source spectra, and this I did. Okay, yeah, this I did using like few different ways. So we had like on-site measurements using a spectroradiometer that directly gives output as a sun spectra, and this measures in 80 channel, and you can like use the finder to focus on the sun, and it measures the sun within like 1 degree opening angle. Then I also use the solar irradiance value and scale them to improve the ASTM spectra, and use the ASTM spectra in combination with the glazing spectrum to calculate different functions. And then another method was using the HDR image capture that was done during the experiments, and using the color HDR images and deriving the color component from these HDR images, and then using eval glare and RCOM to calculate different either V lambda or supplementary photometric functions. So once this was done, like once the spectra was measured, then we tried to apply different V lambda functions from literature. So all of these V lambda functions comes from mainly the transportation literature, where the V lambda was characterized for conditions for nighttime traffic light and the LED headlamps of the vehicles. So this is where they found an impact of color, and then tried to quantify them in terms of VDG, which is the V lambda for discomfort glare. So I tried to apply all of these functions to the data set I had, and you see that all of these functions kind of predict higher sensitivity in the short wavelength range, but most of them have very similar sensitivity in the long wavelength range. And yeah, you can already like see from these curves that they didn't really work on the data set that I had, because in my data set I had much higher discomfort in the long wavelength region as well as in the short. So none of these functions really worked. So this kind of also highlight a more deeper issue, which is that the glare or the perception may not be additive, and it cannot be maybe fully measured with a spectral weighing function alone. So after this, I tried to apply or consider the Helmholtz-Kohl-Rausch effect, which is basically the saturated colors appear more brighter compared to unsaturated color, even though they have equal luminance. So all of these color on top have same luminance, and this is when they are converted to grayscale, but they appear, but the like brightness of all of these colors are quite different how they appear to human eye. And a lot of color appearance model try to quantify this effect and incorporate this effect. So I applied color appearance model that accounts for HK effect in order to quantify brightness, and then try to relate brightness with people's perception of glare, what I found in these experiments here. So first one, the model that I applied was CAM15U, which is based on unrelated stimuli. It has been used earlier in some other glare models, so I thought of trying it out here as well. Unrelated stimuli here means that the color was viewed in isolation. It was not compared with another color. The experiments that were done to develop CAM15U had one single color at a time. There was no background color. It was always either gray or dark. And then also applied CAM18SL model, which is based on unrelated self-luminous stimuli. So it is kind of a modified version of CAM15U, but it is more complex in nature, and it also considers the sources which are self-luminous. So this is also kind of fitting well to the experiments that we had here, where we had the sun, which was colored. So also applied this one here. And then the last one was CIE CAM16 model, which is a journal purpose CAM model recommended by CIE. And to apply all of these models, I also took help of Luke Helwig, which is one of the author that developed the revised version of CIE CAM model. So now looking at the results of these three models, first, when we tried these models with the unmodified luminance, basically the full luminance, they didn't really work. So you see that most of them are saturated here already. So what you see here on the screen is the comparison of these three models for the low transmitted scenario and the high transmitted scenario. Except CAM15U, both CAM16 and 18SL kind of saturates after a point. So this was a bit surprising to find. And this is where the model were applied on unmodified luminance, basically the full luminance of the sun, which was varying from 3 million to 30 million candela per meter square. But looking a bit more deeply into these color models, we found that these were only developed for a very low range of luminance, and they don't really behave well when you go above a certain luminance. So if you look here, this is kind of trying like different luminance and seeing how the colorfulness and the brightness varies for these models. So you can see after a certain point, they start to break down. They start to like go in inverse direction, which was kind of, yeah, very weird to see. And this is also not the intention of these models. This is maybe artifact of math behind the model that doesn't work after a certain point. So after finding this out, we tried to apply these model on a equiluminance area. So instead of considering like full sun luminance, we applied this on 1,000 candela per meter square luminance and then normalized it to the ranges where these models perform well. So here you start to see some interesting results. So especially like if you look at the CAM16 and the CAM18 SL models, they both are predicting the brightness higher for the blue and the red glazing compared to the green and the neutral glazing. And same goes for the high transmittance scenario. But the same cannot be said for the CAM15U, which is kind of predicting similar level of brightness for the red. And for the color neutral glazing, this also has to do how these model computes the brightness using colorfulness as one of their input. So yeah, mainly like both of these models were performing good at these ranges, the CAM18SL and the CAM16 revised version. CAM18SL was even performing better because it was predicting higher brightness for the red color compared to the blue. So this was working quite well. But then there is a need to refine these models further for higher luminance values because so far we only applied it to like 1,000 candela, keeping the source at 1,000 candela per meter square. So and then we found this another CIE supplementary photometry. This is what Jain found somewhere like hidden in one of the CIE reports. So this was published in 2011, where they proposed this equivalent luminance model. And this equivalent luminance considered the HK effect as well. So I also tried to apply this and see if this luminance works. So replacing the normal luminance term with the equivalent luminance, which consider both the chromatic and achromatic adaptation. And applying this again kind of resulted in similar ways. So here is the original data set of the luminance, and here is the modified version. So the modified version does seem to go in the same direction as people's responses, but then it still predicts glare higher for the blue compared to the red. But at least both red and blue are quite high in terms of luminance compared to the green and neutral. So same for the modified DGP, which is based on this equivalent luminance. So again, the glare is predicted high for the blue and the red scenario compared to green and neutral, but not so much for the red. It's still a bit lower than the blue one. So yeah. To summarize, red glazing was the most disturbing, closely followed by the blue glazing in creating discomfort glare, and neutral and green were the most comfortable ones. We also know that the V lambda is not suitable to characterize luminance for a brightly lit colored scenario. Models that account for, sorry. And models that account for the HK effect should be considered to predict glare from the colored scenario. Yeah, this is my last slide. It's okay. It's okay. Yeah. Yeah. And the color appearance model should be considered to predict glare, but then they need more refinement in high luminance ranges, for which, yeah, we don't have any currently any model for such luminances. So need to do more experiments, try to validate, adjust, and develop a new glare model for such scenarios. That's it. Thank you. Uh, so it was one of the term defined by the color appearance model. Uh, so the color appearance model take input as either the tree stimulus value, which is either LMS or XYZ, and it also takes radiance of the light source as an input, and then it provides the measurement of saturation. Yes, it's for the glass, yes. It's for the light source behind the glass, which was the sun, the colored sun. It was 55. Yes, they answered either for the low light level or for the high light level. So each person experienced all four colors, but only one transmittance level. And they were, yeah, like point in time measurement. They did not come back for, yeah. Yeah, so the camera we were using was the LMK calibrated camera, but in the end, I ended up using the sun definition from the spectroradiometer and then rest of the scene from the camera. So I did not use the colored sun from the images.
Thank you, Sneha. Please accept my sincere apologies. You handled it very well. Yeah. Thank you for handling it so well. So next on the schedule is the workshop photo. Greg, do you have an idea of where you want to take that? Oh, you don't have okay. Yes, I can get somebody. I'll ask Ashley to come down. Maybe we could do it against the brick wall there with the light coming. Oh, outside? Okay.